In this screencast, we'll look at the definition of binary search trees and various ways of querying them. A binary search tree is a binary tree, which we have just investigated, that satisfies the binary search tree property. This property has two parts. If y is in the left subtree of x, then y.key is less than or equal to x.key. So here we have x, and this is the left subtree, and y. So y has to be less than or equal to x. The other property is if y is in the right subtree of x, then y.key is greater than or equal to x.key, as you might expect. So we'll do that with a red y here. So a y in the right subtree must have a key greater than or equal to x. So this means, of course, that everything on this side is going to be smaller than x, and everything on this side is going to be larger than x. And notice that y is not just the child. This property applies to any y that's down here. You know, if this is the y down here, it must be less than x. And similar on this side, anything way down there must be greater than the x. So this property makes binary trees offer a useful implementation of the dynamic set ADT, because they're going to support most of the ADT operations fairly efficiently, as we're going to see. So two examples. Let's say we have some data here. Here's one tree. 6, 5 is less than 6, 7 is greater than 6, 2 is less than 5, 5 is equal to 5, so that's okay, and 8 would have to go here because it's greater than 7. That's a fairly balanced looking tree, but you can also have versions that are more degenerate like this. As you can imagine, if data is inserted in sorted order, you're more likely to get these degenerate situations. So those are two examples. When we implement the binary search tree in Java or an object-oriented language, we will usually have an instance variable for the root. So that packages up the whole tree. But most of our operations can recursively treat any of the subnodes as a root. And the implementation of a binary search tree node usually includes not only the left and the right child, but will also include pointers back to the parent, and will of course include any data, the key and the data. So in summary, you know, we'll call this a BST node. We'll have key and possibly data, and the left child and the right child, and the parent. So let's look at how we can query these binary search trees. One way of accessing a tree is to do a traversal, in which you process every node of the tree. It could be printing it out, or it could be applying some procedure to it. And there's different orders you can traverse a tree in. This is all review. As you may know, a pre-order means that you visit the parent before you visit all of its children. Post-order is visit the parent after the children. And in-order will be visit all the left children before you visit the parent, and then visit all the right children. And it turns out that in-order is a particularly important traversal order for binary search trees. And maybe we can see why with a little example here. Here's the procedure for in-order tree walk. If the node is not null, you walk the left, print or process the node you're at, and then walk the right. So let's do that. Okay, node's not null, recurse, walk the left. Not null, recurse, walk the left. Not null, recurse, it's null, come back, process that. Okay, return from that call. In that previous call we were just here, so process that node, and now walk the right, go down here, and of course, you know, its children are null, so it's just going to be printed. When you return for that, that will be processed, and then the top level call will do the walk the right. There's nothing to the left, process that node, process the right. So notice these come out in alphabetical order. So a binary search tree, in-order tree walk, is how you get the data out of the dictionary in order. So we're going to show that the time that this in-order tree walk takes is theta of n. And I'm going to work through the proof of this because it shows a slightly more elaborate substitution proof, what we learned about in the last topic. And also because this is the only operation for binary search trees that is order of n that we're going to look at. All the other ones we're going to look at will be order of the height of the tree. So we can say clearly t of n is big omega of n, because no matter what it does, it's got to process every node in the tree. So it's got to do some constant amount of work at least for every node in the tree. So we just need to show that t of n is big O of n. And we're going to do this using substitution. First, let's consider the base case, t of 0. We're going to say it takes some constant amount of time, greater than 0. That's just to enter, to test, to find out it's nil, and then to exit. So now we need to consider n greater than 0. Let's let x be the root, and let's let k equals number of nodes in left subtree, where k has to be less than n because it doesn't include the root. And then that leaves the right subtree will have n minus k minus 1 nodes, because minus 1 for the root and minus k for what's in the left subtree. So then the recurrence relation for doing this is the amount of time it takes to process the left subtree plus the amount of time it takes to process the right subtree plus whatever the time is for this thing, which is actually different than that. So let's write that out. And here we're going to write less than or equal to. Give us a little more flexibility, and it's because we're doing the big O. So we don't have to prove equal. And we're only proving the other half of the equal because we already took care of one half of that with the omega. So time to process the k nodes in the left subtree plus the time to process the n minus k plus 1 nodes in the right subtree plus whatever work is done at the node itself for some d greater than 0. Okay, we want to show that t of n is big O of n, so we need to make a guess. You know, an algebraic expression we read out that we show by induction is true. And it's not just going to be a simple function of n. This is something that you would probably not come up with a guess without some failed efforts first. So this is going to be the guess. T of n is less than or equal to c plus d n plus c. So for the base case, we have c plus d 0 plus c. We're just plugging in 0 for n, is of course equal to c, which is what we want up here. Now for n greater than 0, let's make the inductive assumption, I'll write this in red, that this thing up here is true for m greater than n. So we have to prove this. We want to derive that, but we're starting with our definition. This is what we know. Okay, so this is the start, and this is what we prove. So let's write out what we start with. Now we can use our inductive assumption. We know that k is less than n because it doesn't include the root, and we certainly know that that's less than n, so that since these are both less than n, the inductive assumption applies, so we can substitute this expression here for any t of m. So here k is playing the role of m, so we're going to write out c plus d k plus c, and then here n minus k plus 1 is playing the role of n, so we're going to write n minus k plus 1 in this position here. Okay, so it's kind of long, but that's what we're doing. Let me write this out. So this is equal to, notice we no longer need any t's in here. This is the whole point of this substitution, is to get rid of those t's. So there's the c plus d from there. there's the k, which is playing the role of the m, plus c. And now we need the one for this thing here. So again, here's the c plus d. And now m is n minus k plus 1. Sorry, that's a minus 1. These little things slip in here. Let me fix that. So there's the n minus k minus 1 corrected. Got to add that c in there. So again, this is playing the role of m. And we need d. So that's by the inductive assumption. Now it's algebra. So let's collect some like terms here. We got c plus d times k and times n minus k minus 1. So putting those together, we get c plus d times this. And these two c's, there's the c there, the c there, the d there, they all come together. Let's simplify this part. K minus k, so we got an n in there, minus 1. And I'm keeping those c's separate for a reason, because now I want to rearrange. So here's c plus d times n, and let's just add one of those c's in there. But we got too many c plus d's, because it's really c plus d times n minus 1, so we got to subtract one of them out. And we still got a c and a d left over there. But I'm adding a c. I am subtracting a c here, and I'm subtracting a d there, and I'm adding a d there. So that c and that c cross out. This minus d and this plus d cross out, and we are left with, which is the exact form of what we were trying to show. Where was that? This right here. So that completes the proof. This part showing that t of n is big O of n, and it was obvious that it's omega of n, so that completes the proof that Inorder tree walk is theta of n. Okay, I'm going to go through the rest of these fairly quickly because they're pretty simple. Here we have searching a binary search tree, and of course we use the binary search tree property, where if you're looking at a node and what you're looking for is the key is smaller than the key at that node, then you go left, because all the nodes with keys smaller are at the left, and if it's larger you go to the right. So a recursive version of that, either you've run out of nodes, the tree was empty, or you fell off the bottom, or you found what you're looking for. In that either case you return. Otherwise, if it's less than, go left. Otherwise, go right. Iterative version is similar. If there's nothing left, or you found it, then you're going to return. Otherwise, as you go through the loop, you keep going left or right. So let's say if you're searching for D, D is bigger than F. Or sorry, D is smaller than F, D is bigger than B. You found it. If you're searching for C, C is smaller than F, C is bigger than D, C is smaller than D, you fall off. So that's how it works. So what's the runtime of this algorithm? Well, there's a big variable we don't know here. We don't know the height of the tree, where the height of one node is 0, the height of that would be 1, this would be 2. So we're going to worry about what the height is later, and we're going to do our analysis in terms of the height, h, rather than in terms of n, the number of nodes. And then later on we will relate n to h. So the analysis is extremely simple. We just notice that no matter what we find, we are following some path from the root to the leaves, possibly stopping before we get down to the bottom, right? So every search is going to be some path down, and the length of that path is bounded from above by h. So we will say that searching is big O of h. Now, why didn't we say theta here? Why did we say big O? Well, sometimes we stop partway down. Well, now let's look at finding the minimum in the dictionary or the maximum in the dictionary. Well, again, we use the binary search tree property that if you're at a node, all the nodes that have smaller keys are to the left and all the ones with larger keys are at the right. So if you start at the root, just keep applying that repeatedly. Just keep going left until there's no more left nodes. That has to be the minimum. And symmetrically, if you're looking for the maximum, just keep going right, like the yellow here, until you hit the maximum rightmost node, and that has to be the maximum. And just like before, those algorithms always follow a path from the root towards a leaf. In this case, they make it all the way to the leaf because you are finding the minimum and the maximum. But we don't know that the leaf is, the particular leaf that you found is at depth h, because it could have been just one hop there, and then there's a whole bunch of stuff over here that makes the height higher. So we're still going to say that this is big O rather than theta of h. Well, now let's look at successor and predecessor. In the dictionary, we might have a key and we want to know what's the next larger key or the next smaller key. We're going to assume that all keys are distinct, and we're going to define the successor of the largest key to be nil and the predecessor of the smallest key to be nil. Like with the min and the max, we can find successors and predecessors without doing any key comparison. And the min and the max, we just went left for min, right for max, and surprisingly we don't have to do any key comparison here because of the organization of the tree. And this is a little harder to understand, but there's two cases to consider. First one is if the node X has a non-empty right subtree, then X's successor is the minimum in its right subtree. Or I'll write it that way, X dot right. So why might that be the case? Well, that's something I want you to think about. That might be asked of you sometime. But think about, for any given node, what are the keys of nodes in the right subtree? Which one of those do you want? Pretty straightforward, really. The second case is when node X has an empty right subtree. And this is more complex. Y is the lowest ancestor of X, whose left child is also an ancestor of X. If you want to see this, think about the fact that if Y is the successor of X, then X is the predecessor of Y. So X is the maximum in Y's left subtree, which is essentially flipping the reasoning to the answer of the last question I just asked you. Also, moving from X to the left up the tree, this would be following right children, reaches nodes that would always have smaller keys than X. And they must be in the left subtree of Y. Because if X is the predecessor of Y, let's say this is Y up here, then X has to be in the left subtree of Y because it's smaller. So anything you find up in that tree is going to have smaller keys than X. So I leave it to you to draw out some examples of this to understand this. We can see pretty straightforward here that the complexity of this tree is going to be, well, all of this stuff can only climb up from a node to a root, and this, it can potentially go all the way down a subtree. So like before, this is going to be big O of H. So maybe let's look at two examples of this. Let's maybe add to this tree G and say that we're looking for the successor of F. And so if X right is not nil, return tree minimum of X right. So it'll just go down there. Yeah, of course, if there was something in between F and G, it would eventually find it down here. So that's the case where this right subtree is not nil. And if it is nil, then, like in this case, let's say we're looking for the successor of D. We're going to say, we're going to initially set Y to be X's parent, this one here. Maybe I'll trace this one out here. So right now y is there. And then while y is not nil and x is y right, in other words, x is the right child of y, keep doing that, keep hopping up. X becomes y, y becomes y's parent. So what that would do is if there were another item here and this was our x, this would hop us up parents until we hit to this where there's no, it's no longer the right subchild of something, it's now the left child of something. So at some point here this loop is going to say y is y's parent. You know, we're taking the y up the tree here. At some point it's going to hop over to here, y is y's parent, but the x is y's right is going to fail because here x is y's left. Again, we're hopping x and y up in tandem, so it's like x is and y is there, and then x and y is there, and at the point where suddenly it becomes the left child rather than the right child, that's the answer. So return y, so it would get that. Okay, so we have min, max, predecessor, successor. Actually, I haven't shown you predecessor, but that will be another problem for you at some point to write the pseudocode for predecessor. And another interesting exercise to think about is if a node in a binary search tree has two children, show its successor has no left child and its predecessor has no right child. That's a fact that we're going to use later on. That concludes our review of some basic queries of binary search trees. And next we're going to go on to how to modify them with insertion and deletion, which will be a little bit more complicated.